Hello, welcome all of you to this course of lecture. What I will be doing in the current and the next few lectures is to discuss about current electricity. Let me first point out that so far you have discussed charges at rest, and what we are going to do in this chapter is to look at charges which are in motion, and that is what we call as current. Now, before I go to physics of currents, let me also tell you that current occurs in nature as well. The most common one being lightning, which occurs due to electric discharge during an electrical storm. See, what happens is this, that when drops of water go and reach the cloud at fairly high height, they essentially become like ice clouds. And when different parts of these clouds they collide with each other, they usually lead to generation of electric current. And such discharge, which we call as lightning, could occur between electrically charged regions of a cloud, or between two clouds, or between a cloud and the ground. Now, of course, you all know that the power of a lightning could be quite significant, because an average bolt of lightning transfers about 15 coulomb of electric charge. Now, I wish to tell you that a coulomb, a single coulomb, is a fairly large amount of electric charge, because you might recall that the charge of an electron is 1.6 into 10 to the power minus 19 coulombs. So, therefore, when I talk about 1 coulomb, it means 10 to the power 19 times the charge in an electron. And if you are talking about a very large lightning, then the amount of charge that is transferred could be as high as something like 300 to 400 coulombs, and a typical potential difference in a lightning could be as high as 200,000 to 500,000 volts, and it can go even up to as high as 30 million volts. In addition to this, another thing that occurs in nature, and with really beautiful consequences, is that sun emits gases and particles which move towards the space at a fairly high speed, and part of which also reaches the earth. And some of these which reach the atmosphere, particularly at the higher atmosphere, they happen to ionize things, and they sort of work in or circulate in the region of atmosphere known as the ionosphere. And this current, they create some beautiful sights known in the northern hemisphere as aurora borealis, or also called the northern lights, and very similar things also happen in the southern hemisphere, which we call as the southern light, or also known as aurora australis. And in fact, I have shown you a image of the aurora borealis in the northern hemisphere from NASA public website, and but they occur in different types of colors. Now, in addition, in nature, there are certain fish, actually 6 categories of fish, prominent among them being eels and catfish, which also emit electric charges. Now, remember that our muscle cells have electric potentials, but in some fish, they sort of evolve into cells which are called electrolyte cells, and which can generate potential differences of the order of 800 to 1000 volts or so. And much smaller scale, even within a human body, we know that many of our body functions, for example, the pumping of blood into our hearts, they take place by signals which arrive there from the brains, and these signals are also electrical in nature, and of course they are much smaller. We will be talking about their magnitude there, but basically these examples that I gave you, they are examples of situations where the current is not steady. So what we are interested are in situations where the current remains steady, and this lecture and the subsequent ones, we would be primarily interested in talking about currents which are steady, and later on we will see that steady currents also become sources of magnetic field. Very loosely speaking, electric current is nothing but flow of charges. This is the formal definition, and let us try to make this a little clearer. Now let me say that I have an arbitrary surface, some area, it does not matter, and suppose I have charges, let us say positive charges, which I will call Q plus, and negative charges group, they are Q minus, and they are passing through this surface. Now, so whatever enters into that surface comes out, so therefore, so this is the charge in, and they are coming out on the other side of that surface. So this is my charge out, obviously that is also equal to Q plus, and this is the Q minus. Now, so the net amount of charge Q which is flowing in is Q plus minus Q minus. Now, supposing these charges were steadily flowing through that surface, then the amount of charge that is going through that surface would be proportional to the time t. So, this is proportional to time t during which we make our observation. So, in other words, the rate at which the charge flows that I will call as the, or define formally as my current, this is equal to Q divided by T. Now, this of course assumes that my flow is steady, but supposing it is not. Now, then I would take the formal definition in a slightly different way, and I will say that take a small time interval delta t. Now, during which the amount of charge that is flows through that surface that I talked about is delta q. Then my current I at that instant around which I have taken that delta t can be defined as limit of delta t going to 0, I take as small as time interval as possible, delta q divided by delta t. You recall from your calculus that this is nothing but my definition of dq by dt. So, this is my formal definition of current. Let us look at what are the units of current. So, note that current is defined as charge divided by time. So, therefore, obviously the unit that I expect is coulomb per second. Actually, so this is given a name ampere. Actually, in SI units, the ampere is defined not as coulomb per second, because coulomb is not a fundamental unit. Ampere is, it is defined in terms of its magnetic effects, but that we'll be talking about in later parts. So ampere is a fundamental unit in. So let's go back to the cases that we talked about. For example, typical household appliances in India. You know that Indian electricity supply is in the range of 220 to 240 volts, and typical current values for household appliances is of the order of a few amperes. So let's say of the order of 5 amperes or so. If you want to compare this with, for instance, the strength of the current that takes place in a lightning, this could be typically several thousand amperes. Aurora borealis that we talked about could also go to millions of amperes. Now on the other side, I talked about certain fish like catfish and eel which give out electric currents. There again the natural things, they are typically about an ampere. On the lower end, the human nervous system gives microamperes. So now that we have talked about the definition of electric current, let me now try to tell you how exactly we look at the flow of currents. Though it is not an exact similarity, but there is a lot of similarity with water flow. Flow of water, for instance, through a pipe. Now remember that, for example, at your homes you have a water faucet, and typically there is a pipe which is going through, and supposing at this end there is a water faucet, and I know that if you open the tap, the water immediately starts coming out. Now what happens is this: we have also observed that there is no time difference between, almost no time difference between the time you open the tap and the water comes out. Now actually what is happening is this, that water is being pushed from one end, but because there is a closed faucet at the other end, it is not able to go and it stopped. And so there is no movement of water physically from here to there, because the pipe is already full of water. Now when you open the faucet, then basically all that happens is the water gets pushed, but almost as soon as you open it, because there is already water at this end, the water starts flowing in there. So the incoming water is pushing the water which is there in this, and of course then the water comes out. Now almost very similar thing happens in electricity, for example at your home. Now you switch on, for example, a light, and you will find that there is no perceptible time difference between the time you switch on the light and the light coming up. And the main reason is again the same thing. In the wire which is there are electric charges already there. So what you did when you pushed the switch is to essentially provide that push like what I showed here. So therefore, what we need to do, because the electrons are already there as a part of the matter, and what we need to do is to essentially push it. So what we will be talking about is how this mechanism of pushing the electrons is arrived at, and how does charges actually flow. So let us look at how is current created. So first thing that you have to recognize is that the ability of a material to conduct electricity depends on the property of the material. We know that there are two types of charges. There are positive charges and negative charges. Now what we require is a separation of charges in order to ensure there is a flow of charge. Now for instance, we could create a static charge by rubbing together two materials. This you have learned in your first lecture on electricity, where we talked about static electricity. For instance, if you rub a piece of amber with animal fur, then of course I generate static electricity, and then if we touch amber to the ground, the current immediately passes through and the static electricity is lost. Of course, this current that we talked about doesn't last for very long, and like the other cases that I mentioned, these are also not currents which can be utilized in any useful way. So this is the way one talks about generating electric current. So let us now come to what type of material are suitable for generating electric current. So first thing that we know is all material consists of atoms and molecules, and so behavior of a material, electrical property or any other property for that matter, depends upon the atoms and molecules which constitute a matter and their interaction. Ability to conduct also depends upon physical condition of the material, for example, pressure, temperature, etc. We will be talking about one or two of these things later, but this is roughly what happens. But for the purpose of electric current, the class of materials that we are interested in are known as conductors. These are typically substances such as silver, copper, aluminum, etc., mostly in solid state, but of course you also have mercury, which at normal temperature is a liquid and is an exception. So these are materials which readily conduct electricity. Now that of course happens if these things are brought into a closed circuit and an electric field is applied. So the reason it happens is that the atoms in a conductor, they have the ability to very easily give up. When I say very easily, it means with very little cost of energy, give up one or more valence electrons. And then this valence electrons, which are contributed by the atoms which comprise that solid, they all belong to the material as a whole and not to that particular atom or atoms to which it belonged. And very frequently we use the word electron gas. So these are also called free electron gas. They are free in the sense that they are not tightly bound to an atom, but they belong to the solid as a whole. So, belong to solid as a whole. Now, this electron gas that we have talked about, when you apply an external electric field, they are free to move, because as we know, charges accelerate in an electric field. Now, in our lectures on electrostatics, we have learned that inside conductors, I cannot have an electric field. So, electrostatics, E inside is 0. What we will see now is that under dynamic condition, this statement will not remain valid. So I will come back to it again, but we will say not true under dynamic condition. Now we have been just talking about current in mostly solids, and in this case, since that is the most common form of electrical conduction, we have been talking about motion of electrons. But let me tell you that conduction or transport of charges do not necessarily happen only with electrons. It can happen even with positive charges, and the typical example is what is known as an electrolyte. You might recall your elementary chemistry a little bit. For example, if I have an electrolytic solution, let us just take a simple situation like a common salt solution. Now I know that these are typical common salt, these are what are known as ionic compounds. The way it happened is this, that these sodium atoms and chlorine atoms have this property that the outside valence electron in sodium atom, for example, was extremely loose, in the sense that it was very weakly bound to sodium atom, and as a result sodium could easily lose that. And when sodium lost an electron, this is one example which you might have seen there. So basically what happens is that if it actually loses an electron and thereby becoming a sodium plus. So I should probably write it as this minus electron, so sodium plus an electron. Now this electron that is there is easily attracted by chlorine. So chlorine very readily agrees to accept this electron in its valence shell, and so the chlorine accepts the electron and becomes a negatively charged chlorine ion. So therefore, what happens in a sodium chloride solution is that we have instead of sodium chloride together as atoms, we have Na plus Cl minus. Now, so suppose I had a situation like this. This is a electrolytic solution. So for my typical example, I am talking about sodium chloride. So let us look at that. Now I insert two electrodes, and I will see that I will need to sort of connect them with a battery. The positive end connected to one of the electrodes, the negative end is connected to the other electrode. So this, in our usual language, this is a positive electrode, also called an anode. This is a negative electrode called a cathode. Now look at this. Since the cathode is negative, the electrode is negative, it has the ability of attracting the sodium plus ions. So the sodium plus ions will start moving in this direction. Now likewise, the chlorine ions would move in the reverse direction. And of course, if there is a current, this would, if there is a closed circuit, this would give rise to a current. But basically, the reason I talked to you was that though generally we talk about electrons being the agent of conducting electricity, we also have the sodium and the chlorine ion. For example, the positive ions can also conduct electricity. And in fact, we will see later on in our lectures on semiconductors that even the absence of electrons, thus the vacancies, which behave like positive charges, they contribute to the electrical current. So now what is the situation in an insulator? In an insulator, unlike the case of a conductor or the case of an electrolyte, for instance, the electrons are tightly bound, and as a result they are not free to move. So tightly bound electrons unlike in the case of a conductor, where we have said that there cannot be under static condition electric field inside a conductor, in case of insulators different distribution of charges occur, and the inside the electric field need not be zero. At this moment I postponed my definition or the properties of what are called semiconductors, because that requires a detailed discussion by itself, but we will come back occasionally to this. So let us look at first the metals or the conductors. Metals are of course conductors, and let us look at what happened in electrostatics. Now suppose I had a piece of metal and let us suppose that this is a sample and these are my two ends, and let us suppose artificially I provided a positive charge plate here and a negative charges here. Now look at what actually happens. The free electrons which are here, they would start moving towards the plate with the positive charge, and you see initially before this happens, because one end had a positively charged plate, the other end has a negatively charged plate, I had essentially created an electric field. But if this is a good conductor, as soon as this happens, this will attract the positive plate will attract the electrons, and of course as a result the negatively charged nature of the other plate will disappear, and the motion of the electrons inside would soon stop. So this is what would happen in static condition. But let us look at it slightly differently. Suppose I had a situation like this, but I did not have a static condition because I had applied an external electric field. So let us draw the external electric field and see what happens. So I have the same situation there. And let us suppose I have an external electric field in which this has been placed. Now you realize immediately electrons would start moving opposite to the direction of the electric field. So that will charge up this side, and so that would make that side positive. The result of this is to create an effective field inside the material. So let us call it E in, and this will go on till the field inside, which was E external to begin with, that has been exactly cancelled and there is no longer any field around there. Now this is precisely what happens, and as a result the picture that emerges out of this is like this: a conductor in an external electric field, the field lines are like this, no field inside, so I have negative charges here, the positive charges there. This is my E external. So basically what is happening is this, that it is the electrons which are moving from the right to the left, creating an effective electric field, and that exactly cancels the external field that we had put the material in, and the net field inside in a static condition is equal to 0. Now suppose I do something more. What I do is I have a method of removing these electrons which come here fast enough. So basically what I am creating is a pump. So let me go back to the same picture again, but create dynamic condition. So the same picture, I had an electric field, and we had seen that this electric field had made this side negative, this side positive. And what I do is this, I have a mechanism, we will discuss more about what mechanism it is later, but supposing there is a method of taking out these electrons and feeding it back there. So creating something like a charge pump, if you like. How we do it, I am not given in this picture, but you might have realized that what we do is to join it by a battery and things like that. But this charge pump removes the electrons almost as soon as they arrive here and then feeds it there. So this has the effect that no electric field, internal electric field will be created. E internal equal to 0 for conductor, which would mean that current would flow regularly, and this is the way charges would flow. So this is the way the current appears. So hence charges will flow. So now that we have talked about that current is basically a flow of charge, and we have seen that though there are situations where both positive and negative charges could flow, most of the time we are restricted to talking about electrons. So let me talk about what about the direction, because we all know that, for example, when I gave the example of water flowing, we also know that it has a direction because it depends upon the way they are being pushed. So direction of current. Now conventionally, in spite of the fact that the electrons contribute for the bulk of the currents in situations that we are interested in, but it has always been defined as the direction of flow of positive charge. So the picture that I gave you a little while back, so I had this situation. So we said that there are these electrons which are moving to this plate. So let me still show that electrons moving in. They are being removed continuously. So the electron is moving in this direction. So according to this definition that I gave you, this is a situation where the direction of current is the reverse direction. So let me say that that is the direction in which the current is flowing. So in other words, the direction of current is defined according to a convention as the direction opposite to the direction in which the negative charges flow, that is the direction in which the positive charges flow. Now notice one thing, that you would immediately notice that we have said current has a direction. However, current, though it has a direction, is not a vector. This is something which needs a little bit of thinking to appreciate. So current I has a direction, but is a scalar, it is not a vector. And this is primarily because it does not satisfy the algebraic law of addition of vectors. We will see how currents are added up, and in fact we will be discussing it at a later stage. So let us look at or go back to our original definition. We said dq by dt is my current. So if I take any arbitrary surface, so the amount of charge that is flowing through any arbitrary surface is related to current by this relationship integral I dt. So we have made a statement that current is not a vector, and we have talked about its unit. So we define a quantity which is related to current but turns out to be a vector. So the current density J is a vector, though current is not a vector. So let me explain how it works. Let us suppose I am talking about a current which is passing through an arbitrary surface. Let me show you a surface here. This, let us suppose, is the end of a wire, cross section of a wire, and the current is entering like this and is leaving from this surface. Like any other definition of density, I define the magnitude of the current density as the amount of current passing through a unit area. So let's first talk about the magnitude and then I will come to what is its direction. So magnitude of J is I divided by area. So this is of course a scalar because current is a scalar, area as we understand is a scalar. Since J is a vector, we need to define its direction. Now you are all aware that if you take an infinitesimal surface area, that area can be made as flat as you want by making the surface area smaller and smaller, and so that I can associate a direction with it. This you have learned even in your mechanics course, for instance. So what we are now saying is this, that we define ds, the direction of the area element, as a direction which is perpendicular to the cross section. Obviously this definition makes sense only if the area is infinitesimally small. Now this direction, now you realize that every surface has two directions, one in which the current is coming in and the other side of the surface is the direction from where the current is coming out. Now we take the direction of ds as that surface, the direction of that surface from which the current is coming out. So, and we define J to be in the direction of current flow. So what does it mean? Supposing I have a wire with this cross section and I have current entering like this. So the positive charges are flowing in this direction. So that is my direction of J. And when the current comes out, it is this surface from where they come out. And so therefore, it is outward normal to this surface. So this is your direction of ds. This implies that J dot ds is positive for positive current. So current is not a vector, but current density, which is a point definition. By point definition, I mean that I take a small enough area, I can make that area as small as I like, so that density is defined as a point function. So at every point in the material, I define the density. So we have seen that under electrostatic condition, there is no field inside a conductor. Now what happens in such a situation? See, the electrons are still free, and so let's write it down. Static condition. So no field inside the material. So what happens is this, that in such a situation, the free electrons themselves have what are known as thermal velocities. Now typical thermal velocity of electrons in a metal is of the order of 10 to the power 6 meter per second. Fairly large velocity. Now what happens inside the metal is this, that these electrons move inside the metal in a random fashion, and let me explain to you what actually happens. So in a metal, there are these ions or atoms which are located. There is a periodicity type of thing, but let's not worry about that. I am drawing essentially a pattern here. So what happens is this, if you take a particular electron, this electron is continuously colliding with atoms or ions and then bouncing back from the atom and then collides with another one. So typically a situation could be like this. If this is an electron, it could go here, then here, then here. So all sorts of things can happen. There is no particular pattern, and let me explain why. This collision is essentially elastic in nature. So these are elastic collision. So we are talking about in the absence of any field inside. So let me say E inside is 0. So elastic collisions take place. Now this is something which is very similar to when, for instance, a very light particle collides against a heavier one. So for instance, a tennis ball bouncing against a wall or a stone bouncing against a truck. So we know that a light particle colliding against a heavier mass bounces back almost with an unchanged speed. Now, and not only that, the direction in which emerge will sort of depend upon what is the direction in which the colliding particle approached the ion, and then of course it comes out, and the result of collision and recollision is such that the electron moves around in all directions. Now if you look at a collection of electrons, because of this random nature, the velocities of the electrons, different electrons, are uncorrelated. Now, so let me write it down. The velocities of different electrons are uncorrelated. Now as a result, supposing I say that Vi, let me put an average sign here, represents the velocity of the ith electron, the average velocity of the ith electron. If I sum it over, I equal to, let's say 1, 2, let's say n number of particles are there, so 1 over n, this is equal to 0. This is equal to 0 because the directions of the velocities are totally uncorrelated. So average velocity of the collection of electrons is 0. So let us return to dynamic condition. Now we have seen that under dynamic condition, the electric field inside need not be 0. So let's say E inside is not equal to 0. Now in such a situation, the electrons, which we said move with a thermal velocity, because of the presence of the electric field inside, are also accelerated. So let's say the electrons are accelerated. The velocity or speed with which they move in is still the thermal velocity, but they are accelerated. What is the result? The result is that the picture that I gave you for the static condition roughly holds, but because of the presence of the electric field, on an average, the collection of electrons would move or drift in a direction opposite to that of the electric field. So, the collection of electrons would move in a direction opposite to that of the electric field. A simple analogy might help understand the situation. Supposing you are in a room and there are chairs, it's a classroom, and a few of you, your eyes are tied and you decide to move around in the room. Now, since you cannot see, you are likely to bump against the chairs. You are also, of course, likely to bump against yourselves, but I assume that for reasons that I will explain, I will assume that you don't collide with each other, but collide with the static chairs. Now, once you have collided with chair, you obviously change your direction and start moving in another direction and again collide with another chair. Now, if the situation where what happened in case of static condition, then after some time, if you look at the positions of all the players in the room, they would be essentially random, which corresponds to the situation the average velocity is equal to 0. Now, let me now assume that there is a door to that room where there is a sound signal that is coming up. Maybe a friend of yours is playing flute there. Now then, since you still cannot see, you will be colliding, but when after collision you want to change the direction of your motion, you are more likely to move towards the direction from where the music is coming. So what happens in such a situation after some time? That the distribution is still roughly random, but on an average, the group of students who are there in that room, they would drift towards the door. And this is essentially the concept of drift velocity. Now, when I told you that let us assume that you don't collide with each other, the analogy is because of this. In this case, my colliding particles are electrons. And the electrons, as we know, can be regarded as point particles when I compare their dimensions with that of ions. Now, since the electrons have negligible volume, so the probability that they collide against each other is almost non-existent. And because of that, we assume that the electron interaction is neglected. Now, so what happens to the expression for drift velocity in our situation? So let us return back to this picture, and I assume that I am considering a parallelepiped with a cross-sectional area A and length L. Now what we are saying is this: all the electrons which are within a volume A times L, so all electrons within a volume A times A will pass through the right this phase. Now in this picture, this is the direction of the electric field, which is also the direction of the current density. And the electrons are on an average moving towards this right, and that is the direction of the drift velocity, which we represent by Vd. Suppose n is my electron density. Then the number of electrons which are in that volume is obviously n into L into A. So this area is A. And the charge that is contained is E times n into L into A. Well, this being electronic charge, the charge would be negative, but in this case I am talking about the magnitude of the charge. So in this case, my E is the magnitude of electronic charge. Which is of course equal to 1.6 into 10 to the minus 19 coulomb. So therefore, the current density is given by Q divided by A times T. This is the amount that has passed through this surface in time t. So therefore, this is given by E times n. A has cancelled out. I am left with L divided by T. So that is my E times n times the magnitude of Vd. Now since the direction is opposite to that of the current density, I write my current density J as equal to minus E times n times Vd. The direction of the current density is opposite to the direction in which the electrons are moving. So what I have basically done today is to define what is electric current, realize that electric current is simply an alternative name for electric charges which are moving, flowing. We have pointed out that it is not a vector. We defined a related quantity called current density, and we realized that current density, because it is a point function, can be regarded as a vector, and we started talking about the concept of a drift velocity, which we will elaborate in more detail next time.